Hello. So my name is Johan. We've been working on relighting radiance fields using the Diffusion model. This is a work in collaboration with Alban from INRIA, Julien from Adobe, now Netflix, Jean-François from Laval University, and George from INRIA. So most of us are here. So if you see any of us, feel free to ask us questions about this work. So I'll start with like a 1-minute background on diffusion models and radiance fields. It's going to go really quick. I think we've all seen results like this, where right now we can take text prompts and generate hyper-realistic images from them. And progress in that field has been extremely quick. Like 10-second explanation, we add noise to images and learn the opposite mapping to go from noise to images. And in that way, we can remove noise bit by bit and generate very realistic pictures. And the way this is trained is by learning a denoising network, quite simply, that takes as input an image plus some noise and learns to predict the noise present in that image. And that's all we need to know for our paper to follow this talk. But what's more interesting than generating pictures from text prompts, at least I think, is generating pictures from inputs that are much more precise from like other images. And we've seen that recently with ControlNet, which generates pictures from input modalities such as depth maps and edge maps like this. And what's really so great about it is that it's trained on data sets that are much smaller because it's just a fine-tuning of an existing model trained on text generation. So this means for researchers like us, this is something that we can actually train and work with. And the way that it works very quickly takes an existing pre-trained network, pre-trained on billions of pictures, freezes it completely, has a copy of a few layers, and fine-tunes these layers with an added input. For example, in this example, it's an edge map. So radiance field is our main topic of interest. So I'll give you a 10-second explanation of radiance field. The idea is we take a set of pictures, say 100 to 200 pictures of a scene, and then we fuse them together with an optimization process to obtain a 3D model in which we can freely move the camera and generate novel views. So unlike traditional 3D assets, this is very, very realistic because we're just directly predicting colors that are accurate because they're pictures. But we can't edit anything in this scene. We can't change the illumination. All the lighting is baked in. So what we'd like to do is be able to change the lighting in this scene. Because if you think about it, even moving an object, we need to update its lighting. So we can't do much with radiance field as is. And the representation we've been working with is Gaussian splatting because it's a great representation because it's very quick, fast for training and also for inference. And a 10-second explanation is that the scene is represented using these Gaussian kernels that are positioned, scaled, and rotated in space. Here they're visualized as spheres. So for each Gaussian, which is soft, we've replaced them with a hard sphere so we can kind of tell how the geometry is built. And for each Gaussian, we assign it a color that's a function of the viewing direction. And this function is implemented with spherical harmonics. So our goal is to relight radiance field. And so there's been lots of progress on relighting nerves, especially. So back in 2020, when it came out, results were great first steps, but we could see there are lots of artifacts and errors. And a few years later, with more modern methods like TensorR, we get really nice results where we can put any environment map and even edit the materials. So when we look back at the very start of radiance field, we had very good results on both simple synthetic objects and also more complex real-world scenes with complex occlusion and BRDF like glass. So why are we not seeing relighting results on such scenes? Why is it always like little plastic Lego trucks? So that's a question that we've been asking ourselves. So we tried to understand why. And so most of these methods on nerf relightings are based on inverse rendering. And inverse rendering, the name says it all. It's the opposite of rendering. Instead of going from geometry and BRDF to picture, you go from picture back to geometry and BRDF. So most works use this approach because it makes complete sense. Especially since that forward rendering of 3D scenes, we understand that really well. And if we have precise geometry and precise BRDFs, we know how to solve the light transport equation almost perfectly, I would dare say, and get hyper-realistic results. But this is given perfect inputs. And with radiance field methods, we simply do not estimate the geometry very well. These are results that we got with a method called Sugar, which is explicitly designed for mesh extraction. And we can see that in this scene, which is pretty complicated. There are lots of reflective materials and many objects and occlusion, but it's still kind of a realistic scenario. We see that there are many errors in the normal maps. Any place there's a reflection, essentially there's a hole in the geometry. And so we've tried these relighting methods on such scenes with more than one object, and what we've observed is that, as you can see, there's a huge hole in the pot because there's an error in the geometry. With another method called relightable 3D Gaussian, we can see that errors in the normal map cause this kind of bumpy surface effect. So this is the problem with inverse rendering methods, is that any sort of error in your geometry or in your BRDF leads to visible artifacts that kind of damage realism. So that's the reason we haven't seen results on complex scenes. So an alternative approach to inverse rendering consists of directly regressing multi-illumination data. So if you have data of the same scene under different illumination conditions, you can directly learn to predict this RGB color, and it will give something that looks great, even if your geometry is really bad, in fact. So in this paper called Nerf in the Wild, what they did is they took popular monuments, where tourists took thousands of pictures of these monuments at different times of day. So this means you have multi-view, multi-illumination data, and you can regress this directly as RGB, and you're going to get realistic, good-looking predictions, even if there are a bunch of errors in your nerve. But that's for outdoor scenes, right? And that's for like popular monuments. So for indoor scenes, it's really tricky to collect multi-view, multi-illumination data. You need to move a light source around. It's very cumbersome. And what we'd really like to do is just capture a normal nerve and then relight it. So what we asked ourselves is, what if we generated multi-illumination data instead of capturing it and use that for relighting? So given that generative models are so effective now, can we use them for relighting? And so the problem one is that we can't edit illumination using generative models quite yet, or at least at the time we started the project. If you try with the text prompt, it's not going to work. You'll say, put the light to the right, and it's going to generate a light bulb. And that's because these are trained on data sets of paired images and text, and which are scraped online. And when we upload pictures online, we don't describe the illumination in that scene. We don't say, this is a picture of my cat, and by the way, the light source is on the right. No one does that. So it doesn't work. So what we did is we took the control net approach and used a data set called a data set of multi-illumination in the wild. And what they did is they found a clever way of capturing real data with varied, of the same scene under different illumination conditions efficiently. And they did that by attaching a narrow directional flash on top of a camera to a motor. So they'll use that motor to point the flash at different spots on the walls and on the ceilings, and use that bright spot as some sort of like light source that illuminates the entire scene. So it gives something like this, where we have the same scene under multiple, there's like a dominant lighting direction that moves around. And what we did is we recovered this principal illumination direction from the light probes in the scene, which gives us an angle. So it's a very coarse form of control over the light. And we train control net on pairs of illumination of the same scene. So what we'll do is we'll take one picture, add noise to it, give it to control net, and it has to predict the denoised version, which actually is predicting the noise within that image, but I'm putting the picture so the diagram is understandable. And as input, we're giving it the target lighting direction, and we're giving it a picture of the same scene under another illumination. So maybe this is a bit confusing because there are like many parts, but it's essentially a normal supervised learning process where the input image is the dark picture there, and at the end we predict that image under the target lighting direction that we feed to control net. So we can, afterwards, we can take an image and move the light within it. So in our preliminary results, they were really quite bad. So control net as input, you always give like depth maps and edge maps and so on. And so you don't have the entire, like the majority of the image like we do. So when we train control net, we would get completely wrong colors. Like things would be purple, green, just about any color you can think of. Like this bottle was green, now it's blue. So what we did to fix this problem was, like we found that this problem occurs because at the beginning of training, when your input image is all noise, it has to predict the noise present in the image, which is the entire image. So it has nothing to learn. It's kind of learning the identity function for the first few steps, and that ends up breaking things. So there's a paper called Common Diffusion Noise Schedules and Sample Steps Are Flawed, and they showed that this caused contrast problems, and we've shown in our paper that it also fixes the color problems. And the other issue we had is this problem with edges being kind of all garbled. If you know anything about stable diffusion, it makes complete sense because there's an encoder and a decoder step that downsamples everything, then re-upsamples it. And the decoder does not know the input image. So we had to adapt things, give the input image to the decoder and fine-tune that. So we used the decoder from this other paper called Designing a Better Asymmetric VQ GAN, which is for image inpainting, but we repurposed it for relighting. And now we get correct edges. So now that we have this, we have our control net network, which is really, really nice results for single image 2D relighting. And so we can only move the dominant direction of illumination, which is kind of limited, but it's also like, it's really realistic because we've trained on real data only. So the input image is in the bottom corner, and now we move the light, but we can't move the viewpoint. So now we arrive at what we initially wanted to do, which is to take this pre-trained control net, we train it once, with its weight, and now we take a nerve capture, and for each image of our capture, we generate a bunch of different illumination directions. So this gives us a sort of virtual or fake multi-view, multi-illumination data set from our initial capture. And then we take this multi-view, multi-illumination capture and feed it to Gaussian splatting, where we've replaced the spherical harmonics with a small MLP that takes as input the lighting directions and predicts the color of the Gaussians. Is this clear? I saw like a confused face here. Anyway, but so essentially it's basically normal Gaussian splatting, but we've replaced spherical harmonics with an MLP. And so there's one problem left. The problem is that our control net network was trained on a single image, trained to work with individual pictures. So when we apply it to a capture like the one on the left, for each frame, we get different predictions. So if I'm to pause this video, each individual frame looks pretty good, but they're all inconsistent with one another. So that's problem number 2, is that radiance field, well, they only work because of multi-view consistency. They're really reliant on it. And so if we train with inconsistent inputs, we get something like this, where there are a bunch of popping artifacts and a bunch of hugely distracting floaters. So the floaters tend to occur very close to the camera. And this was debugged in this other paper called Floaters No More by Julien and Valentin, who are both here. They showed that the gradient scale is different close to the camera than far away. And we've kind of used the intuitions for that paper, but adapted it to Gaussian splatting in a way that's very simplistic by deleting Gaussians that are close to the camera. So anything for each camera, we estimate a Z-near plane, and all the Gaussians that fall in front of it, we just completely delete, which deletes many of the floaters. And now we're only left with these kind of really distracting popping artifacts that are caused by holes in the surface. So to solve these holes, what we did is for each training view, we optimized an auxiliary vector, which is kind of a randomly initialized vector that we let free during optimization. And what this does is that we learn to predict the inconsistencies in the images using the colors of the Gaussians instead of using their position and their scale. So this resolves the issue of having holes in the surface. So once we've been through all that work and we've kind of resolved all the problems one by one, we arrive at our final results where we can take captures of regular nerve captures, like this is just pictures that we took using a DSLR camera under a single illumination, and we can change the viewpoint and change the illumination. Yeah. So the good thing is that it generalizes pretty well. These are just random scenes that we captured, like this is George's kitchen. We didn't kind of cherry pick a data set for this. And it's in real time, so this runs at 30 FPS. But the bad part is that we can only move, we can only nudge the light direction around. We can't like put an environment and so on. An environment map, sorry. So the conclusion is that realistic multi-view relighting is possible with nothing but end-to-end learning. So we didn't use physically based rendering anywhere, even to generate synthetic data. All we did was train on real data. And such an approach is robust to improper geometry and works very well in complex scenes, which other methods do not yet. So in the paper, we compare two different inverse rendering based methods using synthetic scenes. So we use synthetic scenes so we can put a light source in Blender and make the eval easier that way. And we see that even though in our method, sometimes the light direction is wrong, at least in every case, it always kind of looks realistic. There are no glaring artifacts. And so that's essentially our method. The limitation is that it works for indoor scenes, so it was not trained on outdoor scenes, so it will not work in such cases. Control is limited, and sometimes there are very funny inaccuracies. Like, for example, on that plate, it created a very realistic looking highlight. It's just at the wrong place. And it created a very beautiful soft shadow because there was a shelf, outside of the image, there's a second shelf, right? So it cast a shadow there. Of course, there's no second shelf. It just kind of imagined that. So it's a very nice shadow that's just wrong. So, and these are all limitations because we're doing just this kind of a very brute force naive thing of training a learning-based relighting on single images, right? So what comes next? This is where I think things will get interesting in the future because what we've done is essentially build a minimum viable product of learning-based relighting, where things are very realistic, it's very robust, but we have no control over anything. We don't have physical guarantees that what we obtain is correct. And so that's kind of one extreme. And the other extreme is physically based rendering, where we know everything in every detail perfectly. We know the equations of everything, we calculate everything, and we get physically correct results. But we're very sensitive to errors in our inputs. So there's probably a lot of in-between options that have not been explored yet, and we'll see in the next few years what people will be able to come up with, and I think it's going to be really, really interesting. So thank you for your attention. Thing is available online.